So we are live now.
Okay, we can start now, Dr. Pandit.
Okay. A very good morning to all of you. I welcome you all to this Ministry of Earth Sciences 38th live seminar by Dr. Jothiram Vivekanandan. Hereafter, I will refer as Vivek. First of all, I would like to thank Dr. Rajivan, Secretary MOES, for initiating this MOES webinar since the lockdown period. And we have been, there were several talks in this series. This is the 38th one. I am privileged to welcome Dr. Jothiram Vivekanandan. He is a senior scientist in Earth Observing Laboratory, NCAR, Boulder, Colorado, USA. The breadth of his research and development includes polarimetric radar, dual wavelength radar, phased array radar, Lidar, and microwave radiometer. He is a fellow of American Meteorological Society and serves as an associate editor for Radio Science. The 2018 Christian Huygens Medal is awarded to Vivek for his pioneering and groundbreaking work on the microphysical characterization of clouds and precipitation by using advanced remote sensors. Prime examples of his leadership are his development of a dual wavelength radar system created by adding a millimeter wave radar to the NCAR's S-band polarization radar, popularly called as S-POLCA, and his scientific and technical leadership to the development of an NSF-funded cloud radar for Gulf Stream 5 research aircraft. He is a senior radar scientist involved in the development of C-band airborne phased array radar. It is a Doppler dual pole weather radar system for C-130 aircraft. This will enable more accurate weather forecasting. This airborne phased array radar is a transformative technology for weather remote sensing with a number of novel ideas and concepts. So with this brief introduction, I invite Dr. Vivekanandan to deliver his talk on Stratocumulus clouds using radar and Lidar. Dr. Vivek.
Thank you, Dr. Pandit, for a kind introduction. Thank you to MOES for organizing the seminar. Thank you to my team, Lidar team, who worked with me on various aspects of the research. This work I started about 5 years ago. Used to work in S-band radars. Then I became a lead scientist for radar and Lidar. And so I have to learn a number of new things because it's a cloud radars and Lidars, which is something totally new to me. So I thought when I started the work, I'm a newcomer to this area. There are a lot of other scientists. This area has more than 30 years history in this one. What am I going to do as a newcomer? I developed the cloud radar, as Dr. Pandit mentioned, the W-band 3 millimeter radar, very sensitive. I thought we need to develop a better scientific product based on that and using the Lidar. I worked on this research for 5 years to come up with a better technique for cloud droplets detection and also estimation of size and liquid water content. Today's talk, basically we'll have 4 subsections. The first section will describe Stratocumulus cloud. A number of you know clouds in general, rainy cloud, but this is Stratocumulus cloud. Stratocumulus cloud doesn't rain. At the maximum, it produces a drizzle. That's all to it. And we don't have much of in situ observations on the ground. And we should have a lot of airborne sensing for it, for looking at cloud droplet size and few things like that. And these clouds are very shallow. That's how it is. My second part will introduce simulations of radar Lidar observations. The third part will describe development of technique, how you use this simulation methodology, come up with a better way of estimating droplet size, liquid water content. The last section, the fourth part consists of application of the technique to the real measurement in the field. Okay, with that introduction, I would like to share my PowerPoint. Let me see how I do that here. Share my screen. Okay, could you see my entire screen now?
Yeah, we can see. Can you please click the hide button?
Hide button, yes, thank you.
Please go
Okay.
ahead.
Okay, can you see my screen now?
Please bring up your PPT.
PowerPoint, okay. Okay,
Very good. Continue.
Yes.
got it, thank you. Okay, Stratocumulus cloud. How does it look like? This picture looks like this. Stratocumulus clouds are very shallow cloud. At the maximum, it has about 200 to 400 meter thickness. And these clouds are just above the boundary layer and below thermal inversions. They are very contiguous when there's a well coupled the boundary layer. When they are intermittently coupled, we see clouds like that. And these clouds are very prevalent, these types of clouds. These contain cloud droplets at the maximum different droplets. Now, in terms of the cloud statistics, stratocumulus clouds have 23% over the ocean, 12% over the land. It's a quite common cloud type. It's so common, and we need to understand what's the droplet size, how much liquid water content in these clouds, because this determines Earth's radiation budget. It's important type of cloud to understand for radiative transfer effects. And a lot of work goes on in this area. Like I said, cloud depth is less than 100 meter or even about 200 to 400 meter. But as soon as cloud depth becomes more than 100 meter, usually contain the drizzle droplets. Drizzle droplets are, in this case, I say it's more than about 100 micron or so. Drizzle 100 micron, about 0.10 of a millimeter. That's the drizzle drops in my condition. I define like that. Then the drizzle alters how the cumulus cloud, when evaporative cooling, all the dynamics goes on with that. Ends up, there's a lot of work goes on in this for Earth radiation budget for stratocumulus cloud. In terms of the radar or instrumentation, I have used in this study the two types of instruments. One is the radar. I see my pointer here. This is the basically the right wing of a G5 Gulfstream aircraft. It's a jet. It's a pod. It's a pod-based system. Inside this pod, we have a W-band radar, which I designed and built it about 8 years ago. This is a 3.2 centimeter, 94 gigahertz radar, cloud radar. Then inside the airplane is a cabin, as you said, the two boxes here. This is a Lidar. This Lidar is 0.532 micron. That's about green light. You see there is an opening on the top of the fuselage. You can make it up, or see my here the down. The Lidar could look up or down. This Lidar is located in the cabin of the airplane, but the radar is located outside of the airplane in a pod-based system. It has a lens antenna. With that, it has a very good beam width. You can collect the measurements. Now, specifications. The radar, in this case, is a W-band radar, 3 millimeter wavelength radar here. It gets about every 10th of a second, it could measure backscatter and wind measurements, Doppler measurements. It has a gate spacing of 37 meters because it has a quarter of a microsecond pulse width. You can measure very accurately the wind and also the power measurement within a dB. It's a very good sensitivity, better than minus 30 dBz at 1 kilometer. You can do that. And it's a very, very powerful radar what we built. The Lidar itself, Lidar is a green light. It's a very sensitive Lidar. It takes a measurement 0.5 seconds to 2000 sample pulses. It has a sensitivity, very good. Look at the aerosols and cloud droplets. Its a pulse width is 50 nanoseconds. That gives a 7.5 meter resolution. Hence, Lidar gives 7.5 meter resolution along the beam. The radar but 37-meter resolution like that. And so we have these two instruments on the airplane. We can take measurements as we fly either above the cloud or below the cloud. For the references, I shown the papers on that 2015 paper where I described the radars. And the Ed Eloranta has a paper on Lidar. And so you can take a look at it if you need more information on that. Okay, what is the challenge? In a Stratocumulus cloud, if you look at, let me go back, I'm sorry. Okay. In this figure, what we show is the radar reflectivity on the y-axis and the cloud drop liquid water on the x-axis. If you want to estimate a cloud drop in the liquid water content, we should know whether the cloud consists of cloud droplets like that in this area or drizzle droplets. The problem is, in practice, we don't know what the cloud consists of. Does it contain a drizzle or cloud droplets? Even few drizzle droplets makes it as if cloud consists of mainly of high radar dBz values. That means if you don't know whether the cloud consists of cloud droplets or drizzle droplets, using the dBz or reflectivity alone, we can't estimate liquid water content accurately. This is the problem. Hence, we need to know the droplet size. Then we could estimate a better way or more accurately liquid water content. That's a challenge. What is the background? Currently, if you look at in the literature, a lot of power law relations exist. Like I show here, depending upon cloud with the drizzle, there is a A and a B. In this case, coefficients, reflectivity function LWC. You see that here, the various multiplicative factor and exponents. We could do that. The problem with this is we need to know whether it's made of cloud or a drizzle or light drizzle. All the things. If you know that, then you can do something like this. Otherwise, you cannot do it. There's a limitation. Then again, for droplet size, that's more difficult to estimate. For less than minus 17 dBz, it is like a cloud only. There are expressions like this. These are based on some power law fits. And that's all we have, not more than this. Hence, there is not a very good method of estimating droplet size or liquid water content, the current in the current literature. Okay, how do they do that? There are other ways. You have a dual wavelength radars. That means you have a two wavelength radars. We can estimate attenuation or absorption. Using absorption and dBz, we can estimate particle size, liquid water content to a certain extent. Again, that has limitations, or it's more expensive because you need two radars to do this. It has to be beam matched. Many times, it is not that easy to develop a dual wavelength radars with our beam match with a very good sensitivity. It's a lot of technical challenges involved in that. Other way to do this is radiometer. Radiometer gives a total liquid water path. Then could use approximation like that. Total liquid water path with the reflectivity, what the radar you have it. Then you can approximate like this. Liquid water content is could be estimated. Use knowing the radiometer measurement the liquid water path, then radar measurements. And there are methods people use like that, but they're all based on say approximations. But you need to have two different instruments which are different footprints, and it's not that easy to do it. Then there are other techniques. They use radars and Lidar. In the literature, if you look at it, the Colliers paper, 2011 JGR, use a Doppler spectrum because fall velocity, those things could be used to retrieve some of the particle size, concentration. But problem with this is many times ambient winds are it's not easy to figure out. Hence, we need to have fall velocity correct for ambient winds and Doppler velocity. Hence, that is not that easy to do it. There are methodologies to do that, but it's kind of complicated. Then also, they have to assume droplet size distributions. I'm sorry. Droplet size distributions, like a gamma distribution, you have to assume few things like that. But in general, there are many restrictions for estimating liquid water content droplet size using current technology. Now, In summary, what we have here is current technique needs a mathematical form of Droplet spectra. That means we need to know or assume the gamma or exponential log normal DSDs to do this work. Then artificially, you got to partition the droplets in cloud, which is less than 50 micron size, or drizzle more than 50 or 100 micron size like that. Based on the DBZ, they have to do it. That is not that easy to do it. Kind of partitioning it. Then it's all valid only over a restricted range of radar observation. Like that means radar reflectivity can't exceed certain threshold like that. And these are the current limitations of estimating liquid water content, droplet size using remote observations. Now, I'd like to describe my next section, second part 2 here. How do I do this? I need to develop a scattering model to do this. I'm an electrical engineer myself. I know a little bit of microphysics. And so I am well versed in developing simulations of instrumentation. In this case, a radar. This is the backscattered cross sections of various droplet sizes. What you see in the x-axis is the size in micron, and the y-axis are cross sections. The blue curve shows the backscatter cross sections. This Rayleigh here, then becomes a me, then oscillating like that. The red curve shows absorption, extinction, like that. The green here is a ratio between blue to red. That's what this one is. Extinction to backscatter. That's what the green is. This is for doubly band for droplets. Similarly, since I'm using a radar and Lidar, I got to do same cross-section computation for Lidar. That's what it is. What's the Lidar? This is for 0.53 micron. So you can see the blue, again, a backscatter. Then this is less than 0.45 micron. This is almost aerosols here. What's a very small particles. But the problem is here. You see that blue curve here. It is oscillating really wild. It's a small change in droplet size on the y-axis, a large change in cross-section. That is incorrect. This happens because at visible wavelengths, the Lidar refractive index, imaginary part, is almost zero, negligible. Because of that, it happens. Hence, if you do a lot of ensemble averaging, the second curve here shows average cross-sections like that. You can see that. That's very nicely came out. We don't have those big oscillations. Again, here I show the radar extinction, the red is extinction cross-section like that. Sorry. So we have basically the backscatter, extinction, and the ratio extinction backscatter. And these are theoretical computations for droplet sizes. Once we have that, then we could simulate radar and the Lidar backscatter. For that, I need droplet size distributions. These were collected in Southeastern Pacific in 2008 in a field deployment from a C-130. They had a cloud probe, 30 bins and cloud probe here, 1.2 micrometer to 47 micrometer sizes. Then drizzle probe between 62 to about 1600 micron or 63 bins. They had a 1 second droplet spectra, about 4,650 spectra. This arranged in 83 ascending or descending flight profiles are the events. That means I have a very clear picture of Stratocumulus cloud profiles, droplet spectra. That's what I have it. This is a very excellent data set, which I used it for simulating the radar, Lidar observations of Stratocumulus clouds. Okay, I like to show simulations now. This is the 4650, about 4,650 droplet spectra. Each data point corresponds to each droplet spectra here. Sorry, go here. Yeah. The x-axis is a dBz. This is in millimeters per meter cube. y-axis attenuation. As we see here, the red dots corresponds to cloud droplets. The green dots corresponds to drizzle droplets. Drizzle droplets have a larger dBz values. Cloud droplets have smaller dBz values based on the x-axis. The attenuation varies only about up to 4 dB, 0 to 4 dB or so. But the dBz varies more than 40 dB or 50 dB range, huge dynamic range compared to attenuation. Hence, depending upon the size, particle size, drizzle droplets have larger dBz values than cloud droplets. This is where the real problem is. That means we need to know whether a cloud consists of only cloud or drizzle or mixture of drizzle and cloud. This is what we have to know. These are simulations. This is a radar and Lidar, the Lidar measurements here. Y-axis shows the extinction, x-axis the backscatter. You see the linear curve, linear line, basically in this case, is the slope is about 20. This is well known. And so what I'm trying to show here is a validation of my simulations based on existing in the literature. These are things what I expect to say. In the case of Lidar, it should be like this, where there is a linear relation between backscatter and extinction for small droplets. In the case of radar, it should be like that. And with this, I kind of get a confidence my simulations are good so that I can proceed a little bit more in depth. Once I do that, these are actual spectra what we collected in Southeastern Pacific. And the x-axis is number of events, 83 events. Y-axis is the height. You see that dBz measurements, simulated measurements, dBz, they are on the cloud top, they're all quite, first of all, these clouds are less than 200 to 400 meters thick. That's all to it. These are stratocumulus cloud. I'm sorry. You can see on the, okay. On that, as you see, the dBz decreases as you go up, all green colors. This is what I expect, the small droplets in the top. But the liquid water content in the bottom one, Lidar measurements in the bottom one, as you see it, they are large compared to in the bottom of the cloud. Hence, this is the opposite. The dBz values are small in the top of the cloud because of small droplets. At the same time, Lidar observation shows large backscatter because for Lidar, there are optical scattering, large backscatter cross-section that causes large returns for the cloud droplets. Hence, we see that opposite trend in both Lidar and the radar observation. This is consistent with what we see for stratocumulus cloud. Now, scatter plot of liquid water content reflectivity, again simulated. You see the green dots corresponds to drizzle droplets, red dots corresponds to liquid water content. The x-axis, the liquid water content gram per meter cube, y-axis are dBz values. As we expected, drizzle droplets have a large dBz values. Cloud droplets have a smaller dBz values for a given liquid water content. These are consistent with what we expect to see in the case of stratocumulus cloud. Now, this is the key. How do you estimate droplet size? We have radar measurements are simulated, which are proportional to 6th power because Rayleigh scattering. Lidar measurements, optical scattering, basically square, d square. Hence, we define a parameter called RLED, RLES, radar lidar estimated size, or RLED. Both are same in my presentation here. Without assuming any size DST mathematical form, digitally using those measurements for in situ measurements, basically we plotted this for 4,650 droplet DSDs, 1 second droplet DSTs. This is the x-axis in this case corresponds to the parameter what I showed here, radar to lidar, reflectivity ratio in dB scale. This is the size. You can see they are like monotonically increasing. There is no dispersion. because how I defined it. In the case of remote measurements, we are defining a size which is consistent with remote measurement. That is why there's no dispersion in this case. Now, in practice, microphysicists used to deal with like this kind of thing. What they have is effective size or median volume diameter. MEDs I shown here, median volume diameter, related to RLED, or what I showed in the previous curve. Here, RLED shown in the topmost here. They are related if you assume a DSD, which is a gamma or log now to derive one from other. But otherwise, we don't need to do that anymore. These D effective or DME not necessary anymore. For remote observations, what we're using is radar to LiDAR ratios, come up with the size. This is much more suitable for remote observations. And I'm not suggesting don't work with the MED or D effective. They have its own use if you use the in situ measurements. But for remote measurements, what we use is radar LiDAR observations related to a RLED, radar LiDAR estimated droplet size. And this is for remote observations only applies. This is a consistent way how we can do that. Once we do that one, we can use that size to estimate it. Now, this figure shows for 83 ascending, descending in situ profiles. For that, what I show here is basically liquid water content in the top one. As you see my curve here, liquid water contents are basically about larger in the top of the cloud, and particle sizes are smaller, as you see here. These all from simulations or from the in situ measurements from the just I plotted. Whatever I measured the DSTs, I plotted these things. And they're consistent with Stratocumulus profiles. That means it has a lot of liquid in the cloud boundaries and a small liquid in the drizzle area where the bottom of the cloud. Once we have that, then we can do simulations. This is a simulations where y-axis shows LiDAR observation simulated, x-axis shows DBZ simulated. Now, you can see there is no correlation between those two. This is good because this shows the LiDAR and the radar gives independent measurements based on the simulations. That means they're not related. Radar gives you a type of measurement which is not like LiDAR measurements. We can use these two simulated observations, come up with droplet size. That's what I'm going to show now. In the next few slides, to show how I can use this to come up with a methodology. And my section 2 so far described what the simulations are, about using a 4,650 droplet spectra for this Stratocumulus cloud. The next few slides to show the methodology for developing retrieval technique. Okay. The size, what we can retrieve, the LiDAR estimated size is shown in the y-axis, liquid water content. What we can see is, if you know the size, RLED, that is, you can estimate it from the radar LiDAR, then we know whether drizzle or cloud droplets. Then you can estimate liquid water content much easier. Similar to here. Here, what you see in the top picture, I show reflectivity, LWC here. If you know reflectivity, we can do that. Unfortunately, reflectivity could be related to cloud or drizzle. We don't know. That's our problem. But this size, RLED, will give us a precise estimate of droplet size. That way, we know it's a cloud or liquid water content or drizzle. Hence, we can do that. Okay, once we do that, the next slide shows the essence of what I do here. Once we have reflectivity measured, this is the radar. The beta is the LiDAR backscatter. Take those two measurements. This millimeter 6 meter cube reflective measurement. Beta is a median stadian inverse. Take the 1/4 of that, multiply 9, factor 9.12, that will give you the droplet size. Droplet size is shown here in microns, between about 10 microns up to all the way to 160 micron. This is the ratio between radar to lidar ratio. This radar DBZ measurement, lidar backscatter measurement. These are measurable quantities that could relate to droplet size. See, the interesting thing is this is almost like a unique measurement where we can do without assuming DSD, the gamma or a modified gamma or exponential, doesn't matter. We can estimate droplet size. That's the key. Once you know the size, here's liquid water content. What I show here is a DBZ reflectivity normalized by the size, RLED. This is plotted in the x-axis. It's called normalized by RLED. The y-axis liquid water content given as a simple linear relationship like a multiplicative factor, the z norm, that's the y-axis, just intercept. And so we can use this equation. This is the essence of simulation here. So what I did is estimate droplet size using a radar and lidar observations. Then once we know the droplet size, then we can use the DBZ, normalize the droplet size, liquid water content. This is the summary of how we can retrieve droplet size, liquid water content based on simulations. Now we need to validate. How do we validate? We know the truth since we know that measured DSD spectra. From that, we know droplet size, we know liquid water content is known. For that, we selected the DSD profiles from the measurements. We have many, in this case, I got about 82 events. I selected, say in this case, I show two spectra. One is a narrow spectra, the black line, event 1. This contains very small droplets. Then the pink or magenta color, the broader spectra. Hence, I have many types of DSDs in my in situ measurements. I use them for validation here. Here is, I show 4 different profiles where I computed reflectivity, the function of the height. You can see the narrow spectra, a broad spectra, what I showed you earlier. Then the intermediate thing also I have it here. Let me go back. This is the reflectivity simulated, the LiDAR simulated for those profiles for the Stratocumulus cloud. This is the radar to LiDAR ratio. What we see here is interesting. The DBZ values, as we see, it decreases with the height. The LiDAR increases with the height. This is how it's supposed to be, Stratocumulus cloud. And these are consistent. When we say Stratocumulus cloud, yes, it replicates Stratocumulus cloud properties. DBZ decreasing with the height, decreasing with the height. LiDAR increasing with the height. And here we show radar-LiDAR ratios, which are used for estimating droplet size. This LiDAR ratio, which is extinction to a backscatter, basically shows most of them are close 19 or 20. That goes up in small droplets. Now, using that, this is a validation. Figure A, the 6-panel figure. Figure A shows retrieved droplet size. Okay, droplet size, in this case about 30 micron, very small droplets. In this case goes between say about 65 or even 80 microns up to even 30 microns here. Droplet decreases, as you see, decreasing the droplet size as expected at the height. The red curve shows again 90 microns, other things. This magenta color shows much larger droplet size with broader spectra. Now, we know what we retrieved, RLED, based on simulated results. Since I used the simulations, I know what the truth is. In situ measurements, I know. From that, the second curve B shows what's the difference between retrieved minus in situ measurements. Basically, you can see the error is less than 5 micron. That means I'm able to estimate droplet size much better. Less than 5 micron error is very pretty good, very close than what I estimated. The error in percentage is less than 5%. Hence, my retrieved accuracies are better than 5% due to DSD variations. The curve D shows liquid water content. The y-axis is a height, x-axis liquid water content. As we see, the liquid water content increases with the height, which expected in a Stratocumulus cloud. This is the truth versus what I retrieved using those equations, what I showed in the previous graph. The error is less than 0.1 gram per meter cube. These were just 4 different profiles, what I show here. The percentage-wise, you can see the plus minus 50% looks larger. But if you look at average for overall the thing, this is less than a 0.02 gram per meter cube in kind of liquid water content estimate. That's the kind of summary. What I showed the very specific profiles where how the things match up. But overall, if you look at it, this error is even much lower than what I show in this course. Okay, this comes with my last part of the presentation here. Next 10 or 15 minutes, I'll go through how this is being applied to actual field measurement to show that really thing work in practice. Because so far what I showed is only simulations and the validation using a simulation. They're all simulations. But now I'm going to show actual measurements where these things are practically it does apply. Okay, what I did was in 2015 we had a measurements using those lidar what I showed you in the northeastern Pacific. Remember, simulations were done using a southeastern Pacific measurements. They're all stratocumulus cloud, but they're collected in southeastern Pacific. But all the way I came to northeastern Pacific, see where the things does work. That shows how good the technique should be to work in a different area. Now, I got to summarize here. In any situation, we have many instruments. The radar footprint varies between 4 to 35 meters, depending upon, because the 0.7 degree beam width, how far you are from the radar. That footprint varies, 4 to 35 meters. The lidar, the red color here, is a 40 centimeter footprint. Think about like this. You got a 35 meter footprint versus centimeter footprint. And their footprints are different, both lidar and radar. Even though they are the same platform, there's advantage, but the footprints are much different. Then we have a radiometer. G-band, under 93 gigahertz radiometer. They tend to that footprint varies between 10 to 90 meter footprint. And all 3 instruments are remote instruments. What I did was, in this validation, I used the radar and lidar to estimate liquid water content. Then compared with radiometer measurement. It's a totally independent measurement, radiometer, which is 183. See, does it work? If it does validate, if they match, then I got a good technique to estimate liquid water content. That's what it is. Flight track footprint, it goes every half a second, 70 meters, because the airplane flies about 100 feet, goes to about 140 meters per second. And so we have various footprint differences. We try to put them in average into a common footprint, then we can do that. Okay. This is observation here. The topmost, the x-axis shows the time, about 5 minutes of the measurements. In this case, the black line shows where the aircraft flew about 100 meters above the sea surface, looking upwards. This is the radar measurements, W-band radar measurements, about 0 to 2 kilometer cloud top here. This is the dBz values between -30 to about 10 dBz or so, 10 or 15 dBz echo here. You can see here the light drizzle coming up in these 2 cases here, about 3.8, 3.5 or 3.7 minutes. About 2.5 minutes, you can see here the droplets. But this is the cloud boundary here on the top here. That's the top panel, the radar measurements. The middle panel here, the lidar measurement. The lidar clearly shows very strong return. That strong return here, the beta we call it here, backscatter measurements. Very strong. It's a cloud boundary here. You can show that. Lidar picks up the cloud droplets, very good. The radar picks up both the drizzle and cloud droplets and doesn't show very strong returns as we see here, except drizzle case, as we know. And these are the lidar measurements. The bottom panel is the radar measurements corrected for attenuation. You can see that a little bit, this value is a little bit higher compared to this, higher than these values here. In the attenuation corrected W-band measurements, lidar measurements. And so these are the actual measurements over about 42 kilometer swath here for 5 minutes as the aircraft flew. I used these measurements to come up with retrieval. Here it is. The retrieval here is, this is the top left. As you see here, the measurements, what we collected. This panel shows measurements here. This is the retrieved quantities. The top panel shows the size in micrometer, 10 to 5 micrometer here. You can see in the cloud droplets where you can, it's about blue color. This is about 15 micron. It's very small droplets here. Then the drizzle, which contains a lot of big DBC values, that has close to about 500 to 400 micron, about half a millimeter for drizzle droplets. And it's very logically consistent. What we see here is very small droplets, the cloud droplets, drizzle drops, these two large DBC values. Now, we don't have an intercomparison droplet size because we had only one airplane. We don't have other airplane taking the in situ measurements because there is a distance between the aircraft and the cloud. Now, the bottom panel shows liquid water content retrieved. Liquid water content show here is 0.2 to 0.3 gram per meter cube. Here, it's a lot of liquid water content in a cloud area here, cloud boundaries. Then, in the case of drizzle, it's much lower. This is about 10th of or even 0.01 gram per meter cube liquid compared to 0.2 gram per meter cube liquid like that. And it's a very consistent picture. As we see in the Stratocumulus cloud, where the cloud droplets on the top, that shows a lot of liquid, about 0.2 or 0.3 gram per meter cube liquid here, with the very small droplets, 10 to 15 micron droplets here, droplet size. And the drizzle droplets, where drizzling here, consists of very low liquid water content with a large droplet sizes, about 5 micron or so. So it's consistent. Now, the problem is, how do we validate this? For this, we had a radiometer, which picks up the total path, not the profile, like what I show here, the total path. And I summed up liquid water content along every beam like this, every beam like that. Then compare that total liquid water path from the radar and Lidar with the radiometer. Look at it. The radiometer operates independently at 183 gigahertz. There's nothing to do with radar and Lidar, totally independent measurement. Hence, this comparison is, if it does work, it should validate my liquid water content estimate is very good. This is the last but one slide here. Here it shows for the same time frame, the 5 minutes, the red curve is the radiometer, measurements of total path. This is y-axis is a millimeter liquid water path, goes between up to 0.5 millimeters of maximum liquid in this case. The radar and Lidar, the blue curve shown here. I never expected this kind of match with the radar and Lidar, given that I have a moving platform. The footprints of radar is about 20 meters. The Lidar footprint is about 40 centimeters. Then radiometer footprints are about 50 meters. Given different footprints, not only that, radar measures every 10th of a second. The Lidar measures every half a second. The radiometer measures every 6.5 seconds because each instrument has its own time and spatial resolution. I did a pretty good averaging so that I could match as much as possible only along the flight path. I can't do much in the orthogonal to flight path because I can't do much averaging there. Even then, I was able to pick up very good correlation between the blue and the red radiometer, which is 180 gigahertz measurements of liquid water path, and the radar retrieve. This validates the technique. Without this validation, I did all the simulations, retrieval methodology doesn't make any difference. I got to do some kind of comparison where I'm able to match with the radiometer with the water retrieval radar and Lidar. Okay, now this takes me to the last slide here. In summary, I described retrieval technique for dBz between -30 to 0 dBz. In the literature, if you look at it, they're all limited in dBz values. Also, you're going to partition the values. But this technique, what I described here, is much broader in dBz values. It applies to all LiDAR back observation. Then I developed methodology using using simulations from DSD spectra, which are Stratocumulus cloud. I was these objects collected in Southeast Pacific. Then for the 4600 DSD spectra, the errors I showed here is droplet size is a tenth of a micron, what you could estimate. Liquid water content is 0.02 gram per meter cube, like that. And this is due to DST variations. If you able to do this, just DST variations, that means the physics is captured very good. Then comes errors in measurements. That is, it's not added in this. If you add that one, it will increase because the two errors. One is the variation due to DSD, which is captured very well. If you do a very good measurements, then we can reduce the errors due to measurements. And if you add even the measurements of errors due to instrumentation, radar, LiDAR, we could estimate liquid water content within 10% accuracy. That's the thing. Then, like I mentioned before, the simulations are done using Southeastern Pacific observations, but validation is done Northeastern Pacific. That means the physics, what we derived in this methodology, is independent of where you do this measurement, whether it is in whether it's South or Pacific or land, it doesn't matter. As long as if we do these good measurements, then we can do this retrieval. Then the reason why the technique does work is the size. I was able to estimate the size using reflectivity and LiDAR measurements. From that, estimate liquid water content. That means first estimate the size, then the liquid water content using the reflectivity. But that way, reduce the error, because if you don't know the size, using a dBz alone, we can't estimate liquid water content that good. With this, I would stop and take any questions you might have.
Thank you, Dr. Vivek, for a very interesting talk on Lidar and Radar, most of which is indigenously developed, and I hope our audience enjoyed. So we do have some questions. Please wait in the chat box. So you may stop screen share so people can see you.
Let's see. Okay. Let me see. Stop the screen share here. Okay, got it. Okay. I should read out the question here.
Right.
Question 1. How will aerosol present in the mixture of cloud and drizzle droplets in Stratocumulus cloud affect the radar, LiDAR simulations? And what's uncertainty attributed to it? Okay. The aerosol return is almost negligible in the case of backscatter in the radar. In the radar measurements, doesn't even see aerosol. Yes, LiDAR, you would see the aerosol. But in this case, the contribution due to LiDAR backscatter will be about less than a percent or even a tenth of a percent, because we are talking about factor of 2 or factor of 100 to 1,000 compared to return from the radar, from the cloud droplets, the LiDAR. Hence, the aerosol won't affect the technique what I described. Okay. From Mohan Kanwar. Second question. Very nice informative presentation. I have a question. Why LW is high at the top of Stratocumulus cloud? Okay. This is the physics. Stratocumulus clouds are interesting always because of entrainment, how it does it, how this dynamics works out. You see Stratocumulus cloud as a vertical velocity close to about 0.2 to 1 meter per second. There's the cloud top. And the more the ascent, you see the cloud liquid water content is higher in the top of the cloud. That's usually the case where the cloud droplets present. As it rains, it evaporates, virga. Sometimes not rains, or drizzles. Drizzle reaches the ground, but very rarely. And so you expect to see liquid water contents are large, where the cloud droplets present. That's the typical structure Stratocumulus cloud. There are very nice reviews on this one. If you want to take a look at it, it'll be interesting to see it because we used the rain clouds. Even for me, I worked on rain, hail for many, many years. For me, Stratocumulus cloud is something eye-opening. This is a cloud which is very prevalent. It's a much different structure compared to what we expect to see in the rain clouds. Okay. Mokar. Okay. This technique can be extended to other types of clouds. Okay. The answer is yes. Because even though I use this technique to develop Stratocumulus cloud, the reason being Stratocumulus clouds are very small droplets. This is well suited for W band, which is 95 gigahertz lidar measurements. If you look at cumulus cloud and the rainy cloud, you don't penetrate much because of a lot of attenuation. In the technique what I developed, it will work even other type of cloud, provided we're able to you can see those edges of the cloud, maybe a tenuous part of the cloud. It doesn't care. It is only things it has to liquid cloud. That's the only condition. It doesn't apply for ice cloud. Liquid cloud, if you look at a light rain, a light precipitation, it does work, provided you get both lidar and radar measurements coincidentally. That's a key. And the technique will work for other type of cloud. If anyone's interested, I have this thing developed with me with the excellent data sets. I have it with the methodology, the simulation. If someone's interested taking this forward and working with me, I will guide you through this. It's not a problem at all. And someone interested, reach out to me via Dr. Pandithurai, or you have my email on presentation. You can contact me. I can provide you more guidance on this. Okay, I have a question for here. Is it intercomparison necessary before starting the actual observation? Actual observation. Okay, let me understand the question better. Okay, I did two ways. One is I use the simulated observations to get my confidence. Other thing, does it work? Even the simulated observations. Once I got this confidence, then I went to actual measurement, the field measurement, where I don't even know anything about DSDs. I don't know anything about how these clouds are developed. Nothing. All I had was radar observations, then the radiometer observations. And I had these three things. One is the two active measurements, radar measurements, and radiometer observations. With those things, able to validate this. Without the validation, whatever I do, it won't be accepted in the community. That's the key. Hence, I need to validate, because I can't validate using a rain gauge on the ground-based observation, because these clouds rarely rains. It drizzles, it evaporates. Hence, I need to have in-situ observations. In-situ observations are, most of the probes are, very small sampling-wise. They are about, 10 centimeter cube or something like that. Radar footprints are meters. And it's difficult to compare in-situ observations with lidar retrieval because the footprint differences. And I did compare only with comparable footprints. That way, I'm confident what I'm doing is close to what I expect to get it, so that they are consistent. Okay, question number 5, from Madhu Chandra. High lidar for LWC where HCR shows small drops. But lidar observations enter into the scattering that infer bigger drops. Me scattering. Okay. For the lidar, it's cloud droplets always me scattering, because we are talking about 0.5 micron wavelength. The cloud droplets even 10 micron, and they're all me scattering. For the radar, it's in a Rayleigh scattering. And so it's always lidar is going to be scattering. radar going to be in relay scattering. In the two scattering, one is the D6 and the D squared. That's why the independent measurements. The bigger drop, for cloud droplets of even up to 500 micron or 300 micron, you'll be in the relay scattering for a W band. For a Ka band, even at drizzle drops will be in drizzle drops. Even small raindrops will be in relay scattering. It's not a problem. And this technique taking advantage of two different scattering. One is a me, other is a relay scattering. Okay. So question number 6. Have a question. Relation RLED equal to micrometers. Is it empirical? No. It is derived using the simulations. I fitted a power law fit to make it look like that. But basically, if you have all the unit conversions, everything, if you do it, Z is a D6, beta is a D squared. I showed you on the slides. If you go back and take a look at it, you can fit it like this. Hence, it's not empirical based on simulations. It will fit pretty good. And one is D6 by D squared 1/4, same as 9.12. One is a mathematical form, other is a form where you can easily follow this. Thank you for that. It is not empirical, came from the simulations. Question number 7, Panditharai. Okay, Chachin Pandey, the cloud bound. Okay, 1. At the cloud boundary, we see a distinct patch of small cloud droplet size, high relevancy. What does it indicate? Yes, very good question. The cloud droplet size, high liquid water content. Okay, that shows where the LiDAR picks up the cloud boundary. Very good, not a problem at all. That is a key. Now, when the cloud consists of drizzle and cloud, LiDAR doesn't see that. It sees only cloud droplets, because cloud drops cloud drops about typically 100 per centimeter cube cloud droplets. And so you see cloud droplets picked up by LiDAR. Radar won't pick up because radar sees the big drops, drizzle drops. In radar, you don't see that kind of boundary. I have a slides for that. I didn't show you that. But anyway, next time I can show you whenever I have next presentation. And these things are complementary. The LiDAR picks up the cloud droplets. Radar picks up both drizzle and cloud droplets. Okay. Venkata Subramaniam. Okay, if this technique can be extended to other types of clouds, what about the W-band radar measurements during those various types of clouds? I mean about signal saturation, particularly in deep clouds. Okay, we take into account of any signal saturation. Those things are already quality controlled. Hence, our cloud measurements are highly quality controlled. As long as if we have radar measurements and LiDAR measurements, which are good quality control, then we can apply this technique for any type of cloud. Key is the LiDAR measurements. What I showed is the LiDAR is a high spectral resolution LiDAR, and that's the attenuation corrected automatically. And so that is a study. I mean, that's why I have to understand that, because most of the LiDARs are not correct for attenuation, and that is important to have attenuation corrected LiDAR in this case. And the radar measurements are corrected for attenuation. So if you do that, then you get a better estimation. But anyway, that's a secondary. But if you have a good measurement of radar measurements, we can do this. Thank you. Okay. Venkata Subramaniam, if this technique can be extended to other type of cloud, okay, I did that. Okay, Vijay Kumar. In high altitude, if solid hydrometers are present at these heights, how it will affect radar reflectivity? Okay, good question. If you have ice particles, the attenuation due to ice in W band is not much compared to rain clouds. Hence, we got to filter out. If you have super cool liquid, then you can filter out ice from the liquid. Then we can do this technique. Technique what I described is applies only for liquid droplets. Either super cool or non-super cool doesn't matter. As in a liquid, it will apply. Hence, radar reflectivity. We have taken some measurements in southern oceans. Currently, we're looking at it. It's all similar technique when the mixed phase condition exists. That's the ongoing work. Okay, Pradeep Taipa. Okay, I have privilege of visiting your lab 2016. Have you compared these cells with the satellite observations? Which are the present satellite instrument best suited for these observations? I haven't done the comparisons yet. But there are others working on this from other labs, comparing with satellite observations. And we have the work going on in this area with the CloudSat, and there are other satellite observations, infrared satellites, where we have a optical depth measured in terms of liquid water content. That is something we plan to do that in the coming months, or maybe in the future. And this work was on in the University of Washington and also University of Miami. Okay, Matkar, I had another small query. Is it okay to just take the average of radar radiometer observations, wage footprints for co-locations? How about spatial imaging? I mean, every cloud have a spatial homogeneity in the clouds. And sorry. And you got to average out for time and space to get a better better comparisons. And I did those averaging so that almost we can able to get a good spatial temporal comparisons with the radar lidar. Okay, Chachin Deshpande, have you looked into total number concentration close to cloud base and its variation throughout the depth of Stratocumulus cloud? That could be done. This is a good question because I have liquid water content, droplet size. If you assume a exponential or a gamma DSD, then we could estimate number concentration. It requires some kind of assumption of DSD. Then we can do it. And that's a work in progress. We can do that. The problem is comparing with in situ measurements. We don't have two airplanes compared with the number concentrations, droplet size. Maybe in the future experiment, we may have two airplanes where you could compare with the number concentrations with the retrieval technique from radar lidar. And these are all things could be done. It's again, the technique what I described, is published in a JTech. It actually is a yearly release now. If you have access to that, take a look at it. Or if you want a pre-release paper, let me know. I can send you the copy of the paper also. Thank you very much. Appreciate that, your time.
Thank you, Professor Vivek. It was the questions are never ending, so I request audience to contact the speaker. Otherwise, we cannot conclude the session. Thank you very much. It was very informative talk. A lot of appreciation and comments coming in the chat box in the YouTube. So I invite Dr. Pandithurai to say a few words of thanks to Dr. Vivek.
Thank you, Dr. Vivekanandan, for very informative talk, and I also thank all the audience for actively participating and putting out questions. I think there are still some questions which, due to time constraint, we are not posing to you. First of all, I thank Vivek for sitting even midnight. I think it may be midnight in Boulder, Colorado. Thank you very much, Vivek. I also thank our director, Professor Ravi Nanjundaya, for his support, and also Dr. Gopal Iyengar from Ministry of Earth Sciences for coordinating this, and also Dr. Vinu Valsala for excellently coordinating this webinar series. Thank you, Vivek, for your very informative talk, and I think there will be questions coming to your email later. Due to time constraints, we are
thank you, Dr. Vinu, and thanks, Dr. Pandithurai, organizing the meeting and seminar. Thank you very much. I really liked it, and I enjoyed presenting this seminar to the audience.
Okay, thank you. Thank you very much.
Okay, thank you.
Yeah.
Okay.
Thank you.
Computer team, we can go offline now. Thank you.
Okay.